Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is current probes and pressure transducers. What are you missing? So these are probably the two most common accessories that end up going with if you get a scope, got a component test or whatever you want to call it. Current probes and then pressure transducers. And pressure transducers, second most common, I would say, but also often misunderstood as to what we can do with them and how to hook them up and things like that. So we'll cover the tests that we can do and a couple tips and tricks between the both of them as we go through the evening. So first up is going to be current probes, and current probes read current. Go figure. But current could also be expressed as amperage. It's one and the same. You can hear somebody talk about amperage meaning current and current meaning amperage. But when we think about it, as it relates to voltage and resistance, right? And if we want to think about it this way, let's think about like water flowing through a pipe. The electrons, your electricity is like water flowing through a pipe. So voltage is a measure of the pressure going through that pipe of the electricity. So 12 volts, 5 volts, what have you. Amperage or current is going to be a measure of the flow rate of electrons. How much electricity is there? How many electrons are going through? So it's a measure of the rate. So the more is there, the more power you have available. And resistance is the pipe size that the electrons travel through. So if it's a smaller pipe, it's going to decrease the flow rate. Actually, increase the flow, increases the resistance, and the voltage is the pressure too. So we have our little Ohm's law over here, I equals V over R. So current equals voltage over resistance. Current is voltage over resistance. Anyways, in order to test this, we're going to need some of the tools of the trade. So our current probe. So the one in the middle, that is going to be the standard, we call a low amp probe. That's usually like I said, the most common thing that goes with the tool nowadays. And then we also have some other ones that are Snap-on branded, but they are meant more to work with a meter, but they can still be used with the scope, multimeter, graphing multimeter, what have you, because you just plug it into channel 1. So you got ground in channel 1. So the low amp probe goes from about a milliamp up through about 40 amps. And then after that, it's a little above what it's designed to take. Then we get to this one, which is about the next step up. So that one gets you 40 amps to 400 amps is your different scales you're going to read there. And I call that like a medium amp probe, I guess. And then we have the high amp probe over here, which has a 400 amp up to a 2000 amp scale. So that'll read pretty much anything you're going to need to read nowadays with that. So like I said, they are able to be used together with the scope. This one, if you go into the scope and you turn it to a amp probe setting, that's the one it would be calibrated for. These other two, if you're going to use those, you would want to use a voltage setting and then do a conversion, because every every low amp probe out there, even non-snap-on ones, any low amp probe, what it does is it reads the magnetic field that the current induces in the line, reads the magnetic field, has a coil inside, converts that magnetic field into a voltage, and it sends the voltage to the tool. So it's still doing that with this probe. It does the conversion inside the tool. So you would need to use voltage scale. So say this one outputs 100 millivolts per amp, and you're reading 200 millivolts. That means that you're reading 2 amps, right? So it's just you might have to do a little bit of math there depending on what it is. Also note that current probes are directional. This is the one off the low amp probe, and it's got an arrow. The other ones have arrows on them too. As long as the current is flowing in the direction of the arrow, you will get a positive result. So 2 amps, 3 amps, 4 amps, what have you. But current can flow in both directions. So if I have a negative flow, or it's flowing the opposite direction of that arrow, I will get a negative result, minus 2 amps, minus 3 amps, what have you. Now, sometimes you can only fit it one way. So sometimes you need to just kind of put it in there, and then you need to flip it on the screen. So you'll do the invert function on the scope. So a couple different things that we can do with these. So first one, my favorite one, and I know a lot of other people like this one, or once they find out about it, it quickly becomes their favorite one. It's the fuel pump current ramp. Especially if you think you have a bad fuel pump or one that's failing, you can actually see by watching the current flow through the pump what the condition is, how fast it's going, all sorts of different things. Now, this is going to be for brushed traditional electric fuel pumps, right? Because we do have brushless fuel pumps out there. We do have other training on a brushless fuel pump. It's a completely different animal, completely different way to test it. But on a standard brushed fuel pump, pretty much any car that's got a guided component tests available for it's going to have this one. If not, you can just pull up any general one. They're all pretty much the same rule of thumb as to what we're going to be looking for. So we're going to check in guided component tests for the connection instructions. You're going to need to put the jaws around one wire anywhere in the circuit. Now, that's true for anything you're testing with current, just one wire. Because since it reads off of magnetic fields, if it's around 2, 3 wires, like a harness, it's not going to pick up what you're looking for. It's going to pick up a combination of the couple 3 wires. So you want to make sure it's around just one wire at a time. If you can get close to the pump, great, put it there. Otherwise, if it's got just a fuel pump fuse that just powers the fuel pump, pull the fuse in, put a jumper in, put it around that. Same thing with the relay. If we don't have a fuse, we can pull the relay out, put some jumpers in, or just use one of those relays where it's got the little loop on top where you can test it that way as well. And what we're going to see is we're going to see the current flow through the commutator segments on that brushed fuel pump motor. It's an example where the brushes are on the bottom and they make contact, and you can see how they wear out. When they wear out, it might drop out of the pattern, wouldn't send electricity through that coil. Most automotive fuel pumps, I say most because some of them do have 10, but most of them have 8. The vast majority of them that are out there are going to have 8 commutators in the motor. Knowing that, we can watch it as it goes around, and it should look something kind of like this. So each of those bumps is one commutator as it's going by the brushes on them. Now, this one I did on my car, but with about 79,000 miles on it at the time. I went out yesterday and actually got one. It's now at 179,000 miles. So we'll be able to see the difference at 100,000 miles makes on a fuel pump, but that's coming in a minute. So each one of those bumps is one of the commutators. You want to make sure they are fairly rounded. There aren't any missing. A brand spanking new one's going to be more like coming to a point because nothing's worn in yet. Like I said, this is about 79,000 miles on it. You want to make sure they're all fairly even. There aren't any missing. If I had one bump missing there, that would indicate I had one bad commutator segment, and that could cause an intermittent no start problem. Because it'll spin around and then it stops on a good one, and then it's able to flow current again when it starts, and it stops on a good one, flows current, stops on a bad one. Once it stops on the bad one, it's not able to flow current through the bad one that's not making contact, and then it won't spin. And those are the ones where you tap, tap, tap on the bottom of the gas tank, or it takes a bumpy flatbed ride over to the shop, then all of a sudden, miraculously, it starts. So if you suspect that, you would still see that in the pattern. Now, in this case, since we know that there's usually 8 commutator segments, and in this one, I know there are 8 commutator segments. If we count out 8 bumps, that's 1 time around. Now, you can do a rough estimate of the RPM by putting it in a 10 millisecond window, which the guided component test does for us automatically. But because of math, 1 time around in 10 milliseconds would be 6,000 RPM. Now, in this case, it's going about 1.5 times. So I got 8 plus another 4 over here. That means it's turning roughly 9,000 RPM. So we can do, there's an equation for this. Now, if we use the cursors and we measure the distance it takes, or how long it takes to travel 1 time around, in this case, 6.95 milliseconds. So 1 revolution is 6.95 milliseconds. There's 60,000 milliseconds in a minute. So if we take that 60,000 and divide it by how long 1 revolution takes, we get the RPM of the pump, the revolutions per minute. In this case, 60,000 divided by 6.95 gives us 8,633 RPM. Okay. So here's the car at 79,000 miles, the one I just showed you. The one I took yesterday at 179,000 miles, you notice the difference. A lot more round. Here they're kind of spiky. Little spiky, kind of look like a little shark fin, a little rounded on the top. So that's going from the very, very pointy brand new one and kind of wearing in. Now we can see that it's even more worn in, and now they're very rounded. So that is a well worn in pump, but notice nothing's missing. I don't have any noise, nothing really weird going on with the pattern. I'll also note to you that this can vary. This can vary depending on how much fuel's in the tank and things like that. But the RPM is slower. Because you'll notice I don't have nearly as many bumps, and I'm actually at 7.57 milliseconds. So if I want to do the math on that one, 7,900 RPM, right? So it's a little bit, about 1,000 RPM lower. Almost. About 1,300 RPM lower. Yeah, all right. No, less than that. It's slower. that way I can't do the math in my head that quick. But it is turning slower. So there can be some variables. They were both taken at idle. Could have been warmer, could have been cooler. There's a lot of variables. But what you want to understand is a good, healthy fuel pump is going to be 6,000 RPM or greater. One that's on its way out is probably 3,000 or less. And when you get to that 3,000 or less, you're going to get to a volume problem, a fuel delivery problem, because it can't get enough fuel to the front of the car. Pressure is controlled by the regulator. Volume is controlled by the pump speed. So that's why sometimes you can even have variable pump speed. If it demands more fuel at a time, it can speed the pump up, right? So that's how they work. Or like a brushless fuel pump with pulse width modulation, they'll make it spin faster, right? But I just thought it was interesting, the difference. Now these are both taken with AC coupling on, so it just kind of puts the average around 0. So if I wanted to see the actual current, I just turned AC coupling off, and we'll see it gets around 7 amps. That's just at an idle after the car had already started. No real load to stay on the pumps, about 7 amps on a 15 amp circuit. That's on. Next one's ignition coil current ramp. So we'll talk about a couple different ways we can current ramp things, but this is going to show us how the coils are, or the coil is behaving inside the coil. And we can find a bad coil by doing this as well. So we'll put it around the positive side, feeding the coil. And then it should look something like this. We should see a nice smooth ramp. Should look like a ramp, like an actual ramp, right? Comes up. In this case, this is what we call a current limited design. So it stops at about 12 amps and it just levels off. Other manufacturers might just have it go all the way up and down and look like a triangle. So it just goes up until it fires and then it drops off. This is a good one. If it was bad, it would be going up sharply and then over. It shows a high resistance problem inside the coil. Maybe an open, and it's taken a lot more energy to get that coil to charge up. You may also see multi-strike ignition, which would have multiples of these, one after the other. So it's a couple different ways. This is kind of a generalized description. And then if we were to compare that with the ignition pattern, you can see where a dwell starts, where it starts charging the coil. You can see the inrush of current. And then when it fires, the firing line's over here. And then as soon as it fires, well, all that current's got to go away. So, or it goes when it fires. Another one we can do is a relative compression test. This one's pretty popular as well because it's easy to do. You put it around the battery cable, positive or negative, crank the vehicle, make sure that it won't start. So you do a clear flood or disconnect the fuel somehow. But you can crank it over and then you'll be able to see relative to each other. It's not going to give you a pressure, but we're using the starter to crank the motor over. And if it has higher compression, the starter is going to have to work harder. So it's going to have to draw more current. And if it's less compression in the cylinder, it's not going to have to work as hard. So we get a lower spike. So we're going to see this Jeep. It's an 04 Jeep. We're going to see this 04 Jeep a few times throughout this presentation. You'll notice here, though, relative compression. One side is in every other cylinder. Look, one is higher, one's lower, one's higher, one's lower, one's higher, one's lower. So that means I have more compression on one side of the engine, less compression on the other side. Just keep that in mind. Also do fuel injector. All right, so in this case, on this screen right here, I have the voltage, which is the yellow line. I have the current, which is the green line, and then I have the pressure using a pressure probe in the blue line. So I'm actually using all three. So I'm using the thing that back probes that would come with the tool, or use the clips, using a current probe, and I'm using the pressure probe all at the same time to see electrically, mechanically, and hydraulically how is this fuel injector working. So when it turns on, we should see, once again, it should look like a nice ramp. In this case, this is also current limited at about 1 amp. So it drops off. Otherwise, it would go up until it drops off there. This is where the fuel injector actually closes. This is a high point right there. So once it closes, the current stops. What we want to look for on these is going to be this little bump right here. That little bump's where the pintle actually opens, leaves the seat, and starts spraying fuel. Got a better, clearer picture of it over here. So we're going to animate this, right? So it's static until it tells it to turn on. We're going to ground it through the PCM, which energizes the coil, which opens it up, pulls the pintle off the seat, sprays fuel. Notice that dip. So that dip is when this pintle leaves that seat. It has a little bit less resistance at that time. It just kind of overcame it, and then it drops for a second, and then it continues pulling it up. So you should be able to see that consistently in the same spot. Moving up and down erratically, not really opening consistently. You probably have a mechanical problem inside, maybe a spring broken. It's kind of rattling around in there. And then when we remove the ground, we remove the current flow, and it just drops off and then it closes, just like that. So that's current probes. Now let's talk about pressure transducers. Once again, tools of the trade. We have a couple different things here. These are Snap-on ones. There's other companies that make this stuff, but we have what's called a split lead adapter, which can be used on anything with 4 channels. So like a Zeus or a Varus, or even an old school Modus. It has to have that port on it though, on the scope, because that's what powers the whole deal. So if it doesn't have that, you would need to use this one over here. So on like a Triton or a Modus, 2-channel Modus, you need to use this guy over here. They do the same thing. They just interface the pressure probe with the tool. This is 100 PSI, 500 PSI, 5,000 PSI. So how do I hook it up? Well, on the split lead adapter, we need to plug it into that special port on there. On the Zeus Plus, it's actually on the other side of where the color-coded stuff is. It's on the other side. And yes, we know the leads are too short. The new versions that are shipping now have longer leads on them. So they're actually able to fit on both sides of that. That's a little oversight, but we got that fixed. And then you can plug in 2 pressure transducers to that at the same time. Now, I don't know of anybody who's done this, but it makes sense that it would work. It should work. It should be possible. Seeing that we have 4 channels on the scope and we're only using 2, and we have this connector here and we have a duplicate connector right there, I don't see why you couldn't just piggyback 2 of them off each other, right? 2 transducers in there, plug another one in here, 2 more channels, 2 more transducers. I could run 4 transducers. Don't know what you're going to do with 4 transducers. Maybe you want to look at 4 cylinders at once or something like that. That's a possibility. I've never tried it personally, but I would imagine it should work just fine. It's there. So food for thought. And then we have the PSA adapter, which would work for like a 2-channel tool that doesn't have the special connector on there. Or, if you just didn't have it or didn't want to use it. It is powered by 9 volts. Instead of being powered by this connector, it's powered by 9 volts. And you can put 2 pressure probes in there the same way. And then you just put in the channels, channel 1, channel 2. This one does have a ground, so you really can't duplicate them because it doesn't have the extra thing on the ground either to stack them. So this one would just be good for 2 channels. It was actually designed to work with the wireless 2-channel scope. So that's there. So when we have it hooked up, what can we test? So we got fluid pressures like fuel, transmission, hydraulics, anything not over 5,000 psi. You want to use the proper pressure transducer for that. And gas pressures, exhaust back pressure, and compression, which is probably one of the most common things. But back to the fuel injector we were talking about earlier, we got fuel pressure too. So the fuel pressure should be static, fairly static, until that injector opens because it doesn't have anywhere to go. It's just sitting in the rail waiting to go somewhere. So before we open the injector, it should be at whatever the deadhead fuel pressure is. Then when it opens, it should drop off. Now it's probably not going to drop off by a ton because it's not really using all that much fuel. Unless they're really high flow injectors, but it's only using a couple cc's at most of fuel. So it's really not going to drop. The pressure is not going to lose that much. Maybe if you had a volume problem, you might. But the interesting thing is when it closes. So when it closes, that fuel is still trying to go through the injector, and then all of a sudden it's stopped. So at that point, you get a little bump in the pressure because it's kind of just back feeding into the system a little bit. That's why they have dampers on there. And then it levels off and it goes back to where it was. So you got a little dip when it opened, and then a decent sized bump when it was like 5 psi bump when it closed, and then it's everything kind of figures it out. So that's on a known good, normal working regular fuel injector. This is one that we did on, this is a no start Ford Explorer, and you can see there's a 30, that's about 60 something psi down to about 30 psi drop. So that's a 30 psi drop when the injector is open. Now, why would it drop 30 psi when the injector is open? Because the injector was open for 250 milliseconds. That's a quarter of a second. That's an insanely long amount of time. So this had a 5-volt reference problem, which drew the 5-volt signal down, and that made the the coolant temp sensor fail over to like -40, and it thought it was really cold out, so it's adding a lot of fuel. Didn't need it, so it was basically flooding out the engine, and just, once they fixed it, it fixed. But that is pretty drastic drop, and you can see that. You can see it on the gauge; it kind of wiggle back and forth. But in this case, a 30 psi drop. Relative compression, we did it with the low amp probe, and now we can do it with the pressure as well. You want to put it somewhere you can get just like engine vacuum or engine pressure, as it were, in one spot. So in this case, it's a known good. You can see it's fairly even cylinder to cylinder. This is that Jeep again, where it was higher on one side than the other side. So as the odd side was lower and the even side was higher. So large pressure pulse on 1, 3, and 5, and a low vacuum pull on the exhaust part. So what ended up happening on this vehicle is it had a clogged cap on one side. So the exhaust wasn't able to make it out. So it was just kind of piling up and building up back into the engine basically. So we didn't have much of a vacuum pocket, and the exhaust was looking kind of weird. And that brings us to running compression, which is where we can also tell some mechanical issues with a vehicle with that. You can actually tell a lot about just by looking at it, seeing what's going on, if you understand and know what to look at. So this is our compression building up to top dead center. Then we have our ignition phase where it's going to drive the piston back down, pulls it into a bit of a vacuum. Then we have our exhaust phase where the exhaust valves open and then the exhaust goes out. Now you should never see, ideally you should never see the exhausts above 0 psi, because it should just be the exhaust valves are open to the atmosphere and it's just going. If you have a restriction, you might see a buildup in pressure, which we'll see here in a second. Then we have a little bit of overlap with the intake. Intake comes in, builds a little bit of vacuum. Then when the intake valves close, all the valves are closed and it starts building up pressure again. And then we're back to the beginning. Here's an example of a bad one. It's building like no pressure at all. It had like, I don't know, it's no compression really in that cylinder at all. And then we have the one right next to it that wasn't bad, that was firing normally. You can see a huge difference from here to here, right? Big difference, about 60 PSI running. And then you get a little vacuum of, I don't know, about 12, 13, 14, 15, what's it, 16 PSI, negative 16. Exhaust, intake, etc. Here's the one on that Jeep again. So they did 3 different tests on that Jeep. So this is the one where the exhaust pressure was actually building up, ramping up above 0. So it never was making it through that clogged up cap on that side. So you're able to see that. And then here's one I did on my car. You really shouldn't do this with an injector on. You want to make sure the injector is disabled. But I ran for just a few seconds just to get a capture because I wanted to see everything that I could possibly see going on in that cylinder. So we got the yellow is the compression. The blue is a low amp probe on the coil for this cylinder. So I wanted to see where about in the timing it fired. And then the injector as well, where in the timing does that fire? So we see compression. It fires about 20-ish degrees before top dead center. Top dead center happens, it comes down, drives it down, and then we have a little bit of overlap here. And then we have the exhaust. You can see the other pulses from the other cylinders. It's a 4-cylinder as everything's kind of collecting through. We can see those pulses. And then after the injector sprays, you can see we get a bit of turbulence in there as we're getting the overlap from the intake coming in at the same time. So we get a little bit of valve overlap there, and then the intake comes in. There we get draw a vacuum, and then everything closes, and then now we have our compression again. Same deal. Amazing what little things you can see by just adding, and this is why I love using a scope for diagnosis, because you get a picture of what's going on. I can see every little thing that's going on. It's a little over 60 PSI at a peak. The fuel injector is working properly. The coil seems to be working properly. I can see all this detail. That's a lot of detail. And that's on a split lead adapter with a Snap-on 500 PSI pressure transducer. That's just as good, if not better, I don't know, as some other probes I've seen. And people say, oh, Snap-on pressure probes, you can't use it for running compression. You absolutely can. I recommend the 500 over the 100, but definitely seems like I get a little bit better of a picture that way. But yeah, that's pretty clear. You can see an awful lot of stuff going on. Like I said, if you know what to look at. So let's go live. We're going to do a couple things. We're going to do a little different this week. Kind of like what we did last week. So I am going to do this. There we go. All right. So I want to show you my camera here. Because people always ask, how do I hook these things up? How do I hook it up? How do I use it? So we got the low amp probe right here. All right. So I got my Snap-on low amp probe. You see we got 20 amps and 60 amps. 60 amps max. And then you'll also see next to where it says 20 amps, 100 millivolts per amp, with that voltage output I talked about earlier. And the 60 amp scale, it's 10 millivolts per amp. We also have this 0 button. So interesting thing about that 0 button that I didn't really take into consideration till I actually read the manual. Who reads the manual, right? But we do have the manual, and I read the manual, and it says you need to 0 this, not around the wire, which I already knew that, but you also need to hold it the same way it's going to be facing, depending on what you're doing for work. So if I'm going to put it in around the wire and it's going to be like this, I need to 0 it out on that same rough angle. Why? Because it picks up magnetic fields. Earth has a magnetic field. And if we're hitting it at 90 degrees this way, and then we're hitting it at a different angle this way, it's going to affect it. Never thought about that. Never really thought about taking that into consideration. But that's a good tidbit to know. Make sure you do it at the same rough angle and position. And then as far as connecting it, I don't know why I just put that away. As far as connecting it, some people get confused by the colors because we color code everything pretty much but this. So we have a red lead and a ground, right? So the ground's got a stack on it, so I can stack grounds from other leads. So it's got that extra little thing so I can stack another ground on it if I needed to. This one doesn't matter what channel it goes. It doesn't have to go on the red channel, it can go wherever. So if I want it on channel 1, I put it in channel 1. I want it in channel 2, I put it in channel 2. Doesn't really matter. It's not color coded, it's just the color that it ended up being. So you can put it anywhere. It doesn't matter. None of the channels are set up specifically for that. So take that with what you will. Now we got pressure transducer. So I have the, we call it PSA adapter, right? So that's the one that runs off a 9-volt battery. And this was originally designed for the wireless 2-channel scope. So it's got an on-off switch. My battery's dead. But, you take the pressure transducer, which I got right here. And you got a pressure transducer, plugs into the little clip. And then we have this end over here. And that end is keyed, so it only goes in one way. Plug it into the adapter. Same thing with the split lead adapter, it would look the same. Make sure the little mark goes up. And then I would need to plug this into my tool. So we got that. Red is channel 1 and green is channel 2, just so you know. Because we do have different transducer 1 and transducer 2 over there. Like I said, this was originally made for the 2-channel wireless scope, which has red and green, or the channel 1 and channel 2. So they're made to correspond to that, but it'll work with anything that we have that has the capability of reading pressure. Now, how do I hook it up on the other end? So on the other end of the pressure transducer, where you're going to connect it to the car, usually for doing like a running compression or something like that, this is just a standard thread NPT. It's like 3/8 NPT, I believe. And what you want to do is you want to take like a compression hose for a compression gauge, that sort of thing. If you do take one out of a compression gauge set, you're going to want to pull the Schrader valve out just so it gets direct access to the air, the compression coming through out of there. You want to make sure you do that. And then just connect it like you connect a normal compression gauge, except you're reading it digitally. Other thing on this one, since this is from a Zeus Plus, that auxiliary port, like I said, it's on the back. And then the wires would go in the front. So the original split lead adapter that could be sitting in your toolbox won't work with this. The wires aren't long enough. But any of the new ones, they just did a running change on the part. So the ones that are coming out shipping now would have the longer leads on them to make sure it fits on both sides. So just kind of an oversight at the design phase, I guess. Is what it is in that case. All right, now let's take a look at the tool. Let's see, guided component test. So not just guided component test, but inside the guided component test, if you have a snap-on tool with guided component test in it, Zeus, Varus, Modus, Triton, Vantage, any of those, we're going to have these classes. They've been in there for quite some time. They've moved around a little bit. They used to be called top level menus. They used to be hidden in different places, but now they're like right on top. Got the classes right there. Now, if we go into power user tests, first one there is current probe tests. So we got to select a probe, either a generic one, the original one, or the new one. So we'll go in there, and then you see we got fuel. These are just generalized, not vehicle specific stuff, but parasitic draw, for example. It's going to tell you how to hook it up and test for a parasitic draw. Also has the manual, right? So we talked about that 0 adjustment on the manual. Hold the probe in the same direction and inclination as intended for use because of Earth's magnetic field. Crazy. The output 0 offset voltage of the probe may change due to thermal shifts and other environmental conditions like the magnetic field. I think that might have been in here. Yep. So in the talking about error factor. So any device that generates a magnetic field can induce an error. Even the Earth's magnetic field has an influence on current probes. Didn't know that. Now you do. So that's current probes. And then we have pressure transducer tests in here as well. It's going to walk you through a couple different setups, exhaust back pressure, fuel pressure, etc. And then if I go into how-to, there's a bunch of classes. Now, one of these classes happens to be a 10-minute running compression waveform. So it's going to tell you everything that you can see. It's going to give you a couple of small examples there. It's even going to set up the meter to work with it. I don't have it plugged into my tool, so we wouldn't be able to see that. But it's going to tell you, yeah, and this says I use it at 500 PSI in that one as well. So there's a couple other ones in here too. If I go down to like test tips, there's also a where to go, parasitic draw there, as well as pressure transducers here. So for an aftermarket or a snap-on one, going to tell you how to connect it, how to hook it up properly. So a lot of information available within the tool, plus there's vehicle specific tests within the tool to check that out as well. And then one more thing before I let you go, I want to talk about the this capture I took off my car, right? So you can record it, watch it, play it back later in ShopStream Connect, of course. Couple things I want to figure out here though, because we got our compression event, and we got our coil firing right here. So how far before top dead center did that coil fire? Because we know it fires before top dead center. So what it is, I turned on my cursors, and from there to there took 132 milliseconds. Also from there to there, we would know it's 720 degrees, 2 full revolutions of the crank. So if I take my calculator, if I can get my calculator to come up, 132.55 divided by 720 is 0.18 degrees per millisecond. So if I go over here, and I go over here, that's 4 milliseconds. No, that's not right. That's not right. What did I do wrong? 720. I got to tell you the right thing. I do the math. I'm doing this off the top of my head, you know. 20.18. 0.18 milliseconds per degree. Oops. 4.31 divided by 0.18. There we go. 23.9 degrees. Said it was around about 20 degrees, right? 23.9 degrees before top dead center. We would see it there. You can take that measurement as well and divide it by 4, so you know where each of your strokes is, or roughly where each of your strokes is. So it'd be about 132 divided by 4. That'd be every 33 milliseconds on this. So if I wanted to come over, like, that's about half of that. There's almost 30. There's like 33 milliseconds right there, right? So that's 1 stroke. So that's my. You can just divide it down. There's other ways of doing it. I just find it easy enough to do the math, and I just do it that way. All right, that is pressure transducers and car pros. And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.